Welcome to the next video in a course in real analysis. This is lesson 6 on the real axioms and their basic properties. In this video, we will define the concept of completeness, and by giving the axioms of the real numbers, we will say what the real numbers are, and we will give a demo proof of the existence of square root of 2 in the real numbers. So the basic topic here is much awaited. We are finally going to say what the real numbers are, but first, before we can quite do that, we have to say what completeness is. And there are many versions of what completeness can mean in different mathematical settings. Here we're talking about completeness with respect to suprema. So just to give a quick review, we talked before about how if you were to work with the ordered field of the rational numbers, there will be some sets like this one. Here I'm using the notation, the interval from 0 to square root 2, which can be written without the use of square root 2. If you don't like that, I guess I'll just go ahead and describe that as the set of all x in the rationals such that x is at least, let's say, strictly less than, or sorry, greater than 0, and also that x squared should be less than 2. So when I talk about this interval from 0 to root 2, that's what I really mean if I want to write it without using concepts of that come from the real numbers. So anyway, so this is a set of rational numbers. It is bounded above, but it does not have a supremum, and that is a problem which will be fixed by the real numbers. So to set down this definition formally, we can take any poset x ordered by preseq, and we will say that this poset is complete with respect to suprema if for every non-empty subset which has at least one upper bound, then the supremum of that subset exists, right? So if the poset has this property, then the poset has the completeness property, which is sometimes also called the least upper bound property because the supremum is the same thing as the least upper bound. And so now we can state the axiom of the real numbers, which upon a certain kind of counting, there's just one axiom, which is that there exists an ordered field. We will call that ordered field using the symbol, the double struck R, that's the real numbers, and it is complete with respect to suprema. So although that is on one counting, just a single axiom, it's worth appreciating just how much is packed into this one axiom. So we know that, well, it's an ordered field, and even that tells us that it is a field. And that tells us that if you concentrate just on R together with plus, you have a commutative group. Besides that, we also know that R together with plus n times is a commutative ring, and you can go back and recall what that means exactly. But, this is then just all the field stuff. And then on top of that, there's the ordering stuff. And then there's ordered field stuff. And then there's completeness with respect to suprema. So it's just worth reflecting on just how much is really packed into this one axiom. But now that we know that the real numbers exist and we know some basic properties given by the axioms, we would like to try to recover knowledge of all of the familiar facts about the real numbers, the things that one would expect. And one relatively modest starting place for that kind of idea is to show that there is a copy of the natural numbers inside of the real numbers. Well, we know by an axiom that 0 and 1 are both real numbers and they are not equal. And so with that, we could define the number 2 and the number 3 and so on, recovering the notion of natural numbers as a subset of the reals. Now, it's one thing just to kind of list a bunch of elements, but we would really want to know that this set, the elements of this set, really behave in the way that we expect from the natural numbers. However, as I've said a few times now, I won't want to prove any claims like that because we should just take the natural numbers for granted. That's not the kind of thing that is really our interest when studying the real numbers. So if there's enough interest in, proving that this set is isomorphic to the natural numbers or anything like that, then I might make a video later as a kind of optional study, but this is just not our core interest. And so we will just take for granted that these numbers are in the real numbers and that they behave as we expect the natural numbers to behave. All of the same could go just as well for the integers and the rationals. So again, these can be constructed inside of the real numbers, and we can prove that they have the properties that we expect from them. But we won't do that in this video series, at least not as a core part of the video series, if I ever get around to doing it as some optional thing. So if we're skipping over all that kind of stuff, then where do we begin? Well, we want to learn about the distinctive properties of the real numbers, and probably a pretty great and natural place to start is to investigate and try to demonstrate rigorously that this has really gotten us something more than what we had with the rational numbers. So for instance, we would love to demonstrate the existence of an irrational number, which is to say a number that is in R, but is not in Q. Now, in discrete mathematics, it's very standard to demonstrate that square root 2 is not a rational number, but be careful, that does not immediately imply that root 2 is an irrational number, because for all we know, there may be no real number satisfying the properties of root 2. And by the way, when we talk about root 2, what we mean is some number satisfying this equation, x squared is equal to 2, right? We want some number which, when squared, is equal to 2. That's just the very concept of root 2. And at this moment, we have not proved rigorously that such a number exists in the real numbers. So that would be a good place to start with doing some rigorous proofs based on the axioms. So we're going to go ahead and state this as a theorem. Before I do, I'll make clear some notation that will become important. So I'm going to use this superscript greater than or equal to 0 on any set to talk about its non-negative subset. This is very much like the superscript plus notation that I've introduced in another video, but in any case, and this is, by the way, also using interval notation, and intervals are introduced and discussed rigorously in the book. I'm going to, because I think that's relatively easy stuff to process, so I'm not going to talk about that a whole lot. As some further notation, let's just briefly talk about this superscript notation that we are all familiar with. So certainly we understand that when this is a natural number, it means a multiplied with itself n times. Again, the book discusses this thoroughly and rigorously, and so I will just direct you to that if you're interested in it. But I will now proceed to the theorem, which is the claim that there is the number square root 2 in the real numbers. That is to say, the real numbers contain some number which satisfies this equation. So we're about to prove that theorem. Now, I've covered up the proof here to try to encourage you to appreciate how hard it may seem to approach this problem to begin with. So what axioms are going to tell us that the square root of 2 exists? It doesn't seem like any one of them really stands out, but you could think like this. Well, we know that the rational numbers form an ordered field, and they are unable to produce the square root of 2. So whatever it is that is going to give us the square root of 2, it's probably going to have to make essential use of the completeness axiom. And that means we need a set. We need a non-empty set bounded above and somehow related, and we're going to use some intuition here to guide us into choices, but somehow related to the square root of 2. So maybe to get started, a good idea is to draw a picture. Some of what I hope to communicate here is the importance of intuition and thinking pictorially and so on as still a very important part of the process so that you know which moves to make when giving a proof. So anyway, if we think that maybe, roughly speaking, root 2 is somewhere around here on the number line, then it makes good sense to pick a set like the interval from 0 to square root 2. And the supremum of that set is going to, one would expect, be the square root of 2. So let's define this set. And we've seen before how we define a set like this. Maybe not that it matters whether the right end is included or not, because in both cases, the supremum would basically be the right end point. But in any case, so we're going to define the set of all real numbers such that, now let's say that we want 0 less than or equal to x squared less than 2, right? So numbers such that their square gets right up close to 2. That's the idea. Now, if I left it at this, then the set would include some negative numbers, because certainly if you take a number over here and square it, then you're going to get a number over here. And so, anyway, this set is going to include negative numbers. And just for simplicity, let's go ahead and remove those negative numbers. Let's say that we're only talking about the non-negative numbers that are like this. It is perhaps a bit of a simplification to pick that set. And let's now try to show that this set is non-empty bounded above. Of course, intuitively, that's obvious, but we should prove it rigorously. So we'll show that this set is non-empty bounded above. Once we have that, we'll know that its supremum exists. And then we'll go ahead and say at that point that alpha, we'll call that the supremum of the set. And then we'll show that alpha squared is equal to 2, thereby demonstrating that some real number satisfies the equation. And that will be our proof. And so here we have it repeated that this is the set we're interested in. And I am not going to actually show that this is non-empty and bounded above. Rather, I'm going to leave that to the viewer. And I have some guidance about how to do that. The non-empty part should be pretty clear. And in fact, I don't even want to give a hint for that, because I think you'll want to be able to do that on your own. But the bounded part is not completely trivial, so I'll give some guidance about how I recommend showing that it is bounded above. So go ahead and prove as a lemma that for any two numbers assumed to be non-negative, then a is less than b if and only if a squared is less than b squared. This is a good exercise. It's not completely obvious how you do this, but if you think about it enough, hopefully you get to the answer. If you struggle and cannot find the answer, I may, in response to a question in the comments, I may answer it there. But also in, I think, the next video, I'm going to do a whole set of exercises. And in that set of exercises, you'll see me basically prove this and, in fact, something stronger. So, so if you struggle too much with that, you might just watch the next video and that might show you what you need to see. But in any case, try to do it yourself before looking at the solutions that I give. But in any case, once you have all of that, then you can say or show that the set L is, for instance, bounded above by 2. Other numbers would also work, but 2 works. So moving on, and assuming that we now know that L is non-empty and bounded above, then we'll go ahead and set alpha equal to the supremum of L. And now we're going to try to show that alpha squared is equal to 2. So how do we approach this? Well, what we know fundamentally about alpha is that it is the supremum of some set, which is very much a concept that is most directly related to ordering. And it doesn't seem like ordering, and it also doesn't seem like the algebraic axioms, about fields and whatnot, are enough to really tell us that alpha squared would tell us really anything about alpha squared. So anyway, all of this is just to motivate that probably we need to use the ordering relations. And how else are we going to use the ordering relations to show an equality? It's probably got to be that we just rule out that alpha squared is less than 2, and then later on we also rule out the possibility that alpha squared is greater than 2, right? So that's just a bit of motivation for why I think that we should approach this by contradiction. Again, a lot of what I'm trying to communicate here is when you see a problem like this, how do you know what to do? How do you know what the next step is? And so I'm hoping to give some guidance about how to think about these things. But even then, even when we've decided that we're going to assume for contradiction that alpha squared is less than 2, well, where do we go from there? Well, again, right, let's try to look to some geometry and let's develop some intuitions to help guide our next steps. And on the number line, you would kind of expect or imagine that if we're saying that alpha squared is less than 2, you would think that probably alpha is less than root 2. Now, we really immediately go to that. We cannot immediately say that because we cannot take square roots, right? Kind of the point of this is that square roots are not a part of our fundamental toolkit, and so we cannot make a jump like that so quickly. But it certainly seems intuitively like that should be true. Now, assuming that that is true, then what we might sort of do with that intuition is to say, well, then I can probably find some value, let's call it beta, where beta is in between, right? In between alpha and root 2. And what this would mean for us is that, again, working somewhat on intuition here, beta squared should then be less than 2. But if we can show that, right, if we can find a beta that is bigger than alpha, and also beta squared is smaller than 2, this altogether would imply that beta is in L, right, the set L. But then, looking back at alpha, we would know that then alpha is not an upper bound on the set L because there would be a number in L that is bigger. So alpha cannot be an upper bound on the set, and that would derive a contradiction because the supremum is by definition an upper bound. So that would be the source of our contradiction, right? Finding this value beta. But then it's almost like we have just exchanged one problem for another, because the natural next question is, well, then how do we find this beta, right? Again, approaching it directly is not terribly easy, but maybe what you realize is that we might want to talk about this distance between alpha and beta, call that epsilon, and that is kind of like a measure of exactly how far apart alpha and beta are. And then, we could say that beta is equal to alpha plus epsilon. And then when you think, well, if we're talking about beta squared being less than 2, then what we're equivalently talking about is that alpha plus epsilon squared should be less than 2. But now this gives us some algebra to do and some algebra to work on. So if now, so the hunt was on for this value beta, and it's over if we can find this value epsilon, maybe because this allows us to do some algebra. And maybe that's an easier question to answer, and so that's why I'm making this particular move. So we are going to do exactly this, and now we're going to write the hunt is on to try to find a value epsilon such that alpha plus epsilon squared is less than 2. Now from here, a fairly natural thing to do is just to multiply out alpha plus epsilon squared. You get this expression. I think it is, in a sense, we're solving for epsilon, so why don't we take the alpha squared, subtract it to the other side? Seems like a natural move. We are now trying to make a choice of epsilon. This inequality cannot be uniquely solved for epsilon, and it cannot be easily manipulated into something that is about epsilon. And so a sort of, how do we get around this roadblock? Well, one idea is to think about the two terms that each have epsilon in them. And you might try to approach this by saying that I would like each of these terms to be half of the target quantity or less. And so that would effectively mean that you would like that the first term, the 2 alpha epsilon, should be smaller than half of the target quantity, and also that the second term, epsilon squared, would be less than half of the target quantity. Now, the first one is really easy to accomplish. After all, alpha is a positive quantity, and that is something you can prove, but it is easy enough to prove that I won't do that here. And therefore, anyway, we can divide throughout by 2 alpha, and it preserves the order of the direction of the inequality. And so then all we have to do is pick an epsilon that is like this, which we'll see in a little while is not at all hard to do. I mean, this is practically a solution for epsilon, so that's not the hard part. Now, for the other part where we want epsilon squared less than 2 minus alpha squared over 2, well, we don't quite have a solution for epsilon, and we can't take the square root because, again, square roots are not available to us. That's kind of part of the point here, is that it's not one of our fundamental objects like addition and multiplication. And so how do we get around this roadblock? Well, we will ultimately choose epsilon less than 1, right? If we can make sure that however we pick epsilon, we do so with the further constraint that epsilon should be less than 1, then epsilon less than 1 will imply, and you can prove this, you are invited to, but it is easy to show that really it's just multiplying that inequality throughout by epsilon, using the fact that epsilon is going to also be a positive quantity. But anyway, so we will have this constraint, or like we will know this fact. And once we have that, then we can kind of, instead of trying to bound epsilon squared, we could instead just bound epsilon, right? So if we can choose our epsilon such that epsilon, rather than epsilon squared, is less than the target quantity, then that would immediately give us that the same choice of epsilon makes epsilon squared also less than this new target quantity. So anyway, the point is that by making sure that we keep epsilon smaller than 1 strictly, then we will have, then we can simply focus on epsilon, and epsilon squared comes for free, so to speak. So, okay, that is everything we need from epsilon. So if we now form this set, right, this is that first quantity that we said we want epsilon to be smaller than. This is the second quantity, and we're going to also make sure that we put 1 into this set so that when we take the minimum over all of these objects, we are guaranteed to have a number less than or equal to all 3 of them. And then, since we maybe want something that is strictly smaller than all 3 of them, then that's easy enough to produce. You could just divide by 2. But again, I'm not going to go through that any more thoroughly than I just did. So there you have it. I mean, that is effectively the whole proof, right? With this, we now know Like we have satisfied every goal that we have set out for ourselves. Now, one would want to write this proof more thoroughly, right? I have given you sort of like how to think your way through the proof, but I haven't quite written up the proof in a completely sort of professional and finalized way. And part of the reason is that you can find this proof elsewhere. So if you wanted to write down your own proof and compare it to someone else's proof, you could. But it's a good exercise, right? You should try to sort of professionalize this proof on your own. But also, when we get around to the exercises, I'll show how I take these ideas and make them into fully professional proofs. And so I don't want to like give that away just now. I want to encourage you to just try to get some exercise in doing that for yourself. But we can regard this as having successfully accomplished the proof by contradiction. And so we now know that 2 is less than or equal to alpha through this proof by contradiction. Certainly, we want to prove it the other way around. Again, I think these are all good opportunities to get some practice doing proofs. So you should go ahead and do this part of the proof. It should be very similar. You will find that there is a negative sign, but that shouldn't affect things too much when you do it on the other side, because you're going to want to have a positive epsilon such that alpha minus epsilon is within the appropriate band, right? You're going to want this value beta, which is smaller than alpha, and its square will be bigger than 2. Now, there is a little bit of a difference. The contradiction that we reached when we were doing the proof by contradiction just a minute ago was we constructed an element which was in the set and also bigger than alpha, meaning that we got a contradiction from alpha not being an upper bound set. In this version, on this part of the inequality, that's not going to be the nature of the contradiction. It's not going to be that alpha is not an upper bound on the set. Rather, you're going to find some other number, namely beta, which is going to be alpha minus epsilon, such that beta is also an upper bound on the set L. And that will contradict the definition of alpha as the least upper bound. So you're going to find a strictly smaller beta, which is an upper bound on the set L. So that's the nature of the contradiction on this side. But again, this is all a very good exercise, and I think I have hopefully communicated how to try to think through these proofs, and so hopefully you have a good chance of taking a stab at it on your own. And I'd like to end the video with an invitation to ask questions. So if you found anything in this video confusing or in the related portions of the textbook, leave a question as specific as you can make it in the comments to this video. And if I can address it there, I will. If it is a substantial enough question, then I may, if I have time, make a video dedicated to answering it and include it in the playlist.